Welcome back to the sidechannel attack session. Our first talk is single trace sidechannel attack on MPC in the head framework, and the speaker is Julie Godard. Louder? Okay. Our first speaker is Julie Godard. Julie, the stage is yours.
Thanks for the introduction. So this is a joint work with Nicolas Aragon, Philippe Gabory, Antoine Loiseau, and as well as with Julien Maillard. And in this work, we have presented the first side-channel attack on the syndrome decoding in the head algorithm using the threshold computation in the head framework. So let me start with a bit of context. So in 2022, NIST launched a second call for quantum computer-resistant digital signature schemes. This call is currently in its second round. And what is interesting is that among the new candidates, we have seen the emergence of schemes based on MPC protocols. So in the first round, we can see that 8 of the 40 candidates are based on MPC protocols, and this remained the case for 7 of the 40 candidates selected for the second round. So if we look at this timeline, we can see that there have been a lot of improvement on the MPC in the head framework. But here, as I want to focus on the syndrome decoding in the head algorithm in its version it had for the first round, we will be focusing on the threshold framework. So now that I have set the context, we can move on to how to build a signature scheme based on MPC protocols. So first, we need a one-way function, which can be an NP-hard problem like the syndrome decoding problem. Using this function, we can build an MPC protocol, which we can then transform into a zero-knowledge protocol using the MPC in the head paradigm. And finally, by applying the Fiat-Shamir transform, we can get a signature scheme like SD in the head. So let me start with a simplified definition of multi-party computation protocol. So in it, we have a secret, X, which we split into n shares. These shares are given as inputs to the various parties, which will then jointly compute a function f on x, such that the latter return accept if x is indeed a preimage of y by the one-way function f, and rejects otherwise. So now that we have our MPC protocol, we can build the zero-knowledge protocol using the MPC in the head paradigm. So let me first recall what the zero-knowledge protocol is. So it's a protocol in which a prover wants to convince a verifier that he knows a statement, but without revealing anything about that statement. So in the context of MPC protocol, we'll get a zero-knowledge protocol of this form. So on the left, you have the prover, on the right, the verifier. The prover starts by generating and committing his shares, which he then sends to the verifier. The verifier wants to check that the prover is honest, and to do this, he will challenge him twice. First, with a random challenge epsilon that the prover will use as input to its MPC protocol. So more specifically, the prover will simulate in his head all the party PI of the MPC protocol. And during this simulation, he will perform some computation, including that of the broadcast values. And then he will send the shares of the broadcast values, so the share of alpha, to the verifier. The verifier can now construct his second challenge, which is a set of indexes denoting I and containing all the indexes except one. And for all indexes in I, the prover will reveal his views, namely his share of X. And the verifier can finish by running the MPC protocol with the value provided by the prover to check its honesty. And this zero-knowledge protocol has some properties, including soundness. And soundness refers to the probability that a malicious prover will be able to convince the verifier that he knows the secret, even if he does not. So here, the soundness is given by this formula. It consists of the probability that the malicious prover can corrupt the computation of the hidden party, or makes the MPC protocol produce a false positive. And in order to have a sufficiently high soundness, we need to repeat the MPC protocol several times. So let's say 2 times. And this redundancy is a key element for our attack, as it will enable us to get a better accuracy on this secret. So now we just have to apply the Fiat-Shamir transform to get a signature scheme like SD in the head. And as I mentioned earlier, the focus here is on SD in the head in its version using the threshold computation in the head framework, also called TC in the head framework. And the main difference in this framework lies in the sharing of the secret. So here we use linear secret sharing scheme, like the Shamir secret sharing. So now that we have an overview of SD in the head, can take a detailed look of how it works in order to understand how we have built our attack. And to do this, we can look at the characterization of the syndrome decoding problem in the context of MPC protocols. But first, one thing I haven't mentioned earlier is that in the 2022 version of the TC in the Edge framework, we are restricted to using linear function within the MPC protocol. So here, if we consider a vector x as a solution to the syndrome decoding problem, we will have that y is equal to h times x, h being a parity check matrix and y a vector, and that the Hamming weight of x is less than or equal to w. And we can see that this second part is nonlinear. So this is why in SD in the end, it had been shown that this inequality is equivalent to this polynomial equality. So I won't discuss here on why this equivalence holds, but what is important is to focus on the construction of the polynomial S. This polynomial is constructed by Lagrange interpolation of the coordinate of x. So in order to retrieve information about the secret value x, all we need to do is retrieve information about the coefficients of the polynomial S. But in fact, we don't need information about all the coefficients of S. And why? It's because in SD in the head, we assume that h is in standard form. So if we set x as xa, xb, we can see that knowing xa is sufficient to recover xb. So using the same notation for the polynomial S, we will have that knowing sa is sufficient to recover sb. So now that we have properly characterized our problem, we can build the MPC protocol. So here too, I won't go into the detail of how it works, but what particularly interesting is what happens at line 4, when the party locally evaluates the sharings of the polynomial S, Q, and F times P at point RK. And why do we do this? It's because to check the polynomial equality M times Q is equal to P times F, we can use the Schwarzschild lemma, which tells us that if we have this equality at a sufficiently large number of random points, then with high probability, it holds at all points. And the part 5 is just the check of this equality using the multiplication protocol of this paper, and for which we need to sacrifice some values, A, B, C here, and also called beaver triple. But as I say, we are particularly interested here in the line 4 when we do the polynomial evaluation, and more specifically the polynomial evaluation of S. And why? It's because this evaluation uses vector matrix multiplication. And we know that from a side channel perspective, this kind of operation tends to leak information. So this MPC protocol is part of the signature algorithm. In it, we start by generating random sharing of the secret values. After, we can commit the party shares, and then we can derive the third challenge, which corresponds to the randomness of the MPC protocol. So we can note here that the verifier challenges are replaced, that we had for the zero knowledge protocol, are replaced by hash function output. And so this randomness, we can use it as input to the MPC protocol, and more specifically, we simulate the MPC protocol 2 times. So this is where we have the redundancy. After, we can derive the second challenge, which corresponds to the index of non-open party, and we can finish by building the signature from the values computing during this algorithm. But what actually happened in this algorithm is slightly different from what I just presented. Indeed, in the MPC protocol, we don't use these sharings. So let's start by noting input plane as the set of secret value. In SD in the head, the share input plane I is defined as follows. So it's input plane plus the sum over j from 1 to L of Fij being the indexes, times input coefj. Input coefj being randomly sampled from Fq to the size the size of input plane, sorry. So instead of simulating the MPC protocol 2 times on this sharing, we'll be simulating on this input coefj. And then if we replace input plane with SA, as we are interested in here in this variable, we'll have this equality. But if you look at the signature algorithm or at the definition of input plane, SA doesn't appear. In fact, a tweak used in the definition of the syndrome decoding allows us to use SA instead of XA. So as a result, instead of doing the polynomial evaluation on SA, we will be doing it on SA coefj. But since SA coefj is random, knowing side channel information about it doesn't allow us to recover the secret, unless we use this equality. So in blue, we have the public value, in red, the secret value, and in orange, the leaky variable, meaning the variable on which we think we can gather side channel information. So we can see that if indeed we can get side channel information about SA coefj, we will be able to recover SA thanks to the public values. And an interesting point is that this equality is not computing in the SD-INDIAD implementation, but directly comes from the TC-INDIAD framework. And using this equality, we can build our attack in two parts. First, a template attack on the jfmul function. So the jfmul function is a function used in the vector matrix multiplication for polynomial evaluation. And for the second part, we can use the structure of the TC-INDIAD framework to combine all the information. And to do this, we can perform a SASCA, so a soft analytical side channel attack. But before going into the details of this attack, I want to recall some definitions. So first, side channel attack. Side channel attack is an attack enabled by leakage of information from a physical crypto system, like an STM32F427, and it can be achieved by measuring various physical parameters like electromagnetic emissions. So there are several types of side channel attack, but here we want to build a template attack on the jfmul function. So now let's talk about SASCA. So considering X as our secret, in SASCA we want to identify operations that are dependent on the secret data. So here the operations are colored on the trace, and then we want to analyze their intermediate values, so here A and B. And to do this, we start by obtaining the probability distribution of the operations, and we are looking to improve prediction of the secret by modeling a maximum a posteriori problem. And to do this, we can use the belief propagation algorithm, also called BP algorithm, on a factor graph. So let's start by building the factor graph, for example. So the red operation is here represented by this, the orange one is here, and the green one is here. And then, using the BP algorithm, which is a message passing algorithm, we can pass the probability distribution between the factor and variable nodes in order to get at the end the marginal probability of our secret X. So in the same way, we built our graph using this equality. So this is our graph. And we can see here that SA coefj are represented by S0, S1, S2. So why 3 polynomials? It's because for the first security level of SD-INDIAD, the threshold is set as 3. Fij are represented by F0, F1, F2, SA by Si, and the shares of SA by input share 0, 1, and 2. And we can split this graph in two parts. On the left, we will have the vector matrix multiplication, and in brown, we have the reconstruction of our secret SA using this equality. And as we repeat the MPC protocol 2 times, we end up with this graph. So we can see that the same hair power matrix is used at each iteration of our graph, and that each iteration converges towards Si. So here we can clearly see the redundancy of the MPC protocol, which allows us to get a better accuracy on our secret Si. And now that we have our graph, we want to test it in simulation in order to see its robustness. And this is what we have done using a noisy Hamming weight model. So we start by initializing the marginal probability of the variables involved in the jfmul computation, so the variables in orange. And from an Hamming weight model with a Gaussian noise sigma. And this gives us the corresponding figures. So on the left, we have the success rate, the Gaussian noise at the bottom, and the corresponding signal-to-noise ratio at the top. And we can see that for security level 1, we are able to recover all the coefficients of SA for noise level up to 1.4, and for security level 3 and 5 for noise level up to 1.3. But when I show that we have a perfect success rate, that's not really the case, as we are missing 1 coefficient for security level 1 and 2 coefficients for security levels 3 and 5. And this is due to the structure of the air powers matrix, of the first row of the air powers matrix, which consists only of zeros and ones, and this is not sufficient for the BP algorithm to be able to discriminate the right value. But it does provide information about its Hamming weight. So for each coefficient non-recover, we'll have an additional complexity of 70. Why 70? 70 corresponds to the number of elements that had the most representing Hamming weight, meaning an Hamming weight of 4 in the Galois field 256. But this additional complexity remains relatively low, so it's not a real problem for our attack. We can now see how our attack works in practice. To do this, we need to build a template attack, but first we want to be sure that the function jfmul is leaking. And to do this, we have decided to compute the coefficient of determination for jfmul's input and output. And the corresponding figure shows that the output is leaking the most, while the two other operands behave similarly. And once we are confirmed that the function jfmul is leaking, we can build 3 templates on the jfmul function that targets the Hamming weight of its input, so operands 0 and 1, and its output. And to do this, we can train this model with 100,000 training traces, which we split into 90% training traces and 10% validation traces. And then we can use the LDA, so the Fisher linear discriminant analysis, to project our data into a lower dimensional space and as our classifier. And since LDA gives us better results for both 2 and 3 dimensional spaces, we have hoped for the second dimension, as this gives us a visual representation of class separability. So here we can see, for the output, that the classes are easily separable, while for the 2 other operands, the distinction is more difficult. And this is confirmed by looking at the table, where we can see that for the output, we have a near-perfect Hamming weight template accuracy, and respectively 0.4 and 0.5 for operands 0 and 1. And we can note that in the polynomial evaluation of SA, SA is behind the operand 0. So we are in the least favorable case. So we can move on to a practical attack. We have decided to derive 3 attacks, one using leakage on the output and on the operand 0, another using leakage on the operand 0, and the last one using leakage on the output. And we want to use a graph and to look at how the coefficient of SA converge depending on the number of epochs of the BP algorithm. So this is what is shown here for the first attack and for the 3 security levels of SD in the head. So we can see that the coefficients quickly converge in 7 epochs. And another thing that we can notice here is that we can see the coefficient that have trouble discriminating to the right value. So 1 coefficient for security level 1 and 2 coefficients for security levels 3 and 5. And of the 3 attacks we derived, only the one using leakage on the operand 0 fails, which is consistent looking at its template accuracy. The other 2 succeeds in just a few minutes. So we can finish by discussing countermeasures. So for countermeasure, we can follow the reasoning of this paper, which presents a Saska on HQC, as we are targeting the same function, meaning the vector matrix multiplication. So following their approach, we concluded that a good countermeasure is full shuffling, which consists of core shuffling and window shuffling. So in core shuffling, we can shuffle the rows and columns together in the air powers matrix. And in the window shuffling, we want to compute each window, so each iteration of our graph, in a random order, allowing us to change the order of the coefficient in the computation of SA. And these countermeasures allows us to achieve a complexity of at least 2 to the power 1200 for the 3 security levels of SD in the head. So to conclude, we presented here the first side channel attack on SD in the head using the TC in the head framework. So we built our attack in 2 parts. The template attack on the jfmul function, which is dependent of the implementation, and the Saska using the threshold computation in the head framework along with the redundancy of the MPC protocol and which is independent of the implementation. So in simulation, we have seen that we were able to recover the secret key from noise level up to 1.4 for security level 1 and noise level up to 1.3 for security levels 3 and 5. And in practice, 2 of the 3 derived attacks succeed in just a few minutes, and we concluded by discussing full shuffling and effective countermeasure. And I can finish by discussing future work. So following the evolution of improvement on the MPC in the 8 framework, we have decided to focus on the frameworks on which the second round candidates are based, and more specifically on the vol in the 8 framework. And thanks for your attention.
Very much for the nice talk. Are there any questions from the audience? Okay, then I'll start. Can you go back to slide 29, I think it was? The one that shows the factor graph?
This one?
Yeah. So I assume that you split this up and get a non-acyclic graph, a cyclic graph,
yeah.
To save computation time?
Yeah, so there is some improvement that can be done on this graph. We can use a node with 4 variables for the brown part, allowing us to have a acyclic graph instead of a cyclic graph. So we don't look at this for now, but we think that it will improve the results, but just a bit, so we don't go through it. But yeah, it can be part of future works.
Do you have any idea how expensive that would be? Probably a lot, right?
For now, because we don't look this way, but yeah.
Thank you. And maybe I can ask another one if there are no questions. Does it work? Okay. Another question. Did you look into the shuffling countermeasures, whether they can be circumvented using belief propagation?
Sorry, what?
Whether the shuffling countermeasures can be circumvented using techniques in the belief propagation?
So for countermeasure, we don't really work on that part. We just follow the paper using doing a Saska and HQC, because we didn't have the time to look at it. And so for now, I don't have an answer for this.
Okay, thank you. Then let's thank the speaker again.